Laura Rodríguez. Hola Laura, ¿cómo estás?
Hola, estoy bien,
Bienvenida.
gracias.
¿Qué tal? Bienvenida Laura.
Gracias.
Bueno, si quieres, entonces vamos a compartir la pantalla para que podamos arrancar.
Um, can we do this in English? Spanish is not the best.
I confused with your name.
I know. I wasn't. I
I
wasn't.
think that you speak Spanish
I
because you
wasn't
name so
raised to.
Spanish.
They
Laura
didn't speak to
Rodríguez,
me in
entonces
Spanish.
I suppose that you speak Spanish also. Okay,
Un poquito.
okay, let's start with the speech of Laura Rodríguez, an investigation of in the feasibility for coupling phantom phosphite oxidation with organic phosphorylation in aqueous solutions under early earth conditions. Thank you very much for your speech, and the public is yours.
Thank you.
Thank
Hi, everyone. My name is Laura Rodriguez. I am a postdoc at NASA JPL working with Dr. Lori Barge. And today I'm going to be talking about my reactions to try and couple the Fenton phosphate reaction to organic phosphorylation under early Earth conditions. So phosphorus is really important for life as we know it. On the early Earth, its most stable form would have been orthophosphate or PO4. Unfortunately, phosphate readily crashes out of solution and forms minerals when cations are present. And what this diagram is showing here is that at a wide range of pH, you have to contend with several different cations crashing out the phosphate. So at higher pHs, calcium will sequester the phosphate and form apatite. If you start to lower the pH, you'll start releasing phosphate, but then you have to deal with ferrous iron chelating the phosphate, forming vivianite. And as you release the phosphate by lowering the pH, then you have to contend with the ferric minerals as well. So this has led to the idea that phosphate may have been more present within mineral matrices than actually dissolved and available for prebiotic reactions. On top of that, phosphorylating or adding a phosphate group to an organic is inherently thermodynamically unfavorable in water. And that's because this is a dehydration reaction. By that, I mean we generate water as a side product. And when you generate water in a solution filled with water molecules, that pushes equilibrium to the left in favoring the reactants. So several solutions have been proposed for these issues, but I'm going to be talking about the potential for phosphite. So phosphite, shown here, is the reduced form of phosphate. It's more soluble than phosphate when cations are present, so you may not have that insolubility issue. It's also relatively resistant to oxidation back to phosphate, so you could have had large reservoirs of phosphite on early Earth. And you can easily get it from reduction of phosphate using ferrous minerals and heat or lightning strikes. So how do we go from phosphite to phosphorylation? One potential avenue is coupling the Fenton reaction with oxidation of phosphite. So this is the Fenton reaction. It's when you react peroxide with ferrous iron, you generate ferric iron and hydroxyl radicals. The hydroxyl radicals can react with phosphite, producing phosphite radicals that can then react with hydroxyl radicals to form phosphate. And then when you have both, you can have phosphate and phosphite radicals combined to form pyrophosphate, triphosphate, and trimetaphosphate. And these polyphosphates are of interest because they can phosphorylate organics in water. So the question then is, can we actually couple this to phosphorylate something in water? And one potential issue we may run into is if we generate hydroxyl radicals in this reaction. And hydroxyl radicals can react with the organics and completely destroy the very organic you want to phosphorylate. So in this research, we were investigating conditions to see if there would be a sweet spot for phosphorylation, defined as where we optimize the amount of polyphosphates being formed, but minimize the amount of the organic being degraded. And to do this, we tested iron versus manganese facilitated reactions. Notably, the reaction I just showed you, coupling Fenton with phosphite oxidation, has only been shown with dissolved iron. So we wanted to see if manganese could also do it. Manganese is of interest because it's an antioxidant, so it could preserve the organic from degradation. Both would have been available on the early Earth. And then we're also going to compare dissolved metals versus their oxyhydroxide counterparts. That's just if you raise the pH, the iron and manganese crashes out and forms these oxyhydroxide minerals. We wanted to see if they're actually crashed out in the mineral matrix, can they still facilitate this reaction? So what I did is I made solutions using ferrous chloride or manganese chloride, added it to solutions of phosphite, sometimes glycerol, and titrated the pH to 5, 6.5, or 8. I oxidized it using peroxide solutions titrated to the appropriate pH, let the reaction go. And then before analysis by NMR, I raised the pH by adding sodium hydroxide to completely crash out the mineral and any residual metals. Centrifuge, took the supernatant and analyzed using phosphorus and proton NMR. So first I'm going to be talking about the results using ferrous oxyhydroxide. So this would be at pH 8, where essentially all of the iron has crashed out into that mineral. So this is phosphorus NMR, the pH 8 reaction at room temperature versus 70 C. These peaks here correspond to our starting reactant phosphite. This here is a PA or phosphonoacetic acid. And we see two new products, phosphate and pyrophosphate. So we see them in both reactions. So this tells us that even if it's trapped in the mineral, it can facilitate these reactions. It also tells us that raising the temperature didn't increase oxidation yields, and in fact promoted the degradation of pyrophosphate back to phosphate. When we added glycerol, we did not see any peaks corresponding to phosphorylated glycerol. So then when we looked at these reactions at various pHs, we wanted to see how the pH had an impact. We plot here the percent yields of phosphate shown in solid lines or pyrophosphate shown in the dashed lines, and the color corresponds to the pH. And what you can see here in general is the phosphate is generated a lot more compared to pyrophosphate. And the pyrophosphate, the pH trends is that the pH doesn't seem to have a significant impact on the yields of pyrophosphate. You would think that pH 5, which is the peach line, would have a significantly more pyrophosphate compared to the pH 6.5 and 8, where all of the iron is like crashed out. And then when we look at the phosphate trends, same thing for the first 2 time points. There isn't a significant difference due to pH, but in the end, the solutions at pH 8 generated more phosphate compared to those at 5 or 6.5, which is just the opposite of what we'd expect since you have all of your iron taken out of solution versus at pH 5 where it's all present in solution. Then we wanted to see what was happening to the glycerol, so we did proton NMR. This is showing a reaction mixture with glycerol and phosphite, but no peroxide to just test the stability of glycerol. We don't see any new peaks, so that tells us that glycerol is stable. When we add peroxide and get the reaction going, we see the formation of new peaks shown with asterisks, and they have shifts consistent with oxidation products of glycerol. And in the literature, there's actually a lot of studies that have talked about how glycerol can react with hydroxyl radicals to form a range of organics. And we think this large peak here is probably formate. So then we wanted to see what about the manganese reactions. So this is phosphorus NMR at pH 5, 6.5, and 8 after a month. And what we see is that the manganese can facilitate the reaction of coupling the Fenton phosphite oxidation reaction. So we see the production of phosphate in all of the reaction conditions. And then at pH 5 only, we start to see this new peak corresponding to pyrophosphate. So notably, the pH 5 reaction was much more efficient at oxidizing the phosphite compared to the higher pHs. And that's more along the trend that we actually expect. So looking at the proton NMR, this is manganese solutions at pH 5 versus 6.5. And we see here the formation of 2 new peaks for the pH 5 reactions. And this large peak here is the same as that in the iron that we think is formate. Notably, at pH 6.5, we did not see any new peaks, especially this peak of interest here. And we didn't see any new peaks in the pH 8 reactions even after a month either. And notice that these are reactions at 2 different time points. This is at 24 hours. This is after a month. I'm comparing them because they have similar phosphite oxidation yields, 8% versus 4%. So if this phosphite was being oxidized through the same mechanism, you would expect this peak to be present here, but maybe at like 50% intensity or slightly less. But we don't see it at all. So that suggests that it's a different mechanism that's proceeding with these oxyhydroxides. And that's actually consistent with previous work that's looked at Fenton reactions facilitated by manganese. They found that when you do the reaction at pH greater than 6, you generate reductants and not hydroxyl radicals. And what's interesting is that pH that's greater than 6, the manganese is actually crashing out and forming oxyhydroxide. So if you do it at pH less than 6, you form hydroxyl radicals. But when you have the mineral present, you don't. And the reductants they think that are actually formed in such reactions are those shown here. And then lastly, we wanted to compare iron versus manganese. So this is plotting percent yields, combined phosphate and pyrophosphate over time and days. The solid lines are iron, the dashed lines are manganese. And what we see here is in general, the iron solutions are better at oxidizing phosphite to the phosphates. Although the pH 5 manganese reaction does eventually get yields on par with the ferrous reactions after about a month. And this leads me to my second point, which is that the reaction is basically complete for the ferrous, facilitated reactions after about a week, whereas the manganese is still going after a month at both pH 5, and then you can see it's slightly increasing even more slowly for the 6.5 and 8 reactions. So iron is much more efficient at oxidizing the phosphite. So in conclusion, metals that are trapped in the oxyhydroxides can still facilitate these reactions. And the oxyhydroxide minerals seem to be most conducive for potentially phosphorylation. So this ternary diagram is really summarizing all of the results. You can think of the right corner here as conditions that really promote formation of polyphosphates, but also degradation of your organic. So that include all of the iron solutions we looked at and the manganese at pH 5. The other corner here is that we generate phosphate but no polyphosphates, but we also have minimal organic degradation. So that would be the manganese oxyhydroxide reactions. And in the middle would be that sweet spot that we're trying to look for, where you have a lot of polyphosphates but minimal organic degradation. And we think that potentially one avenue to get there is using mixed mineral systems of ferrous and manganese. And that's what we plan on testing next. So the ferrous iron could promote formation of the polyphosphate, and the manganese could promote or prevent the organic from being degraded. And I would like to thank my advisor, Dr. Lori Barge, and our collaborators, and you all for your attention, and I'm happy to take any questions.
Okay, Laura, thank you for your speech.
Hi, Laura. This is Francisco Faul from Universidad del Atlántico. And we have a question from our audience I would like to make to you. And the question is, what is your opinion about the importance of phosphine as a bioindicator for the recent case of its presence on Venus?
Phosphine. So phosphine is the most reduced form of phosphorus. I was looking at phosphite, which is slightly more oxidized. But in terms of phosphine, I have a lot of issues with that study. Several people have actually not even been able to reproduce the detection of phosphine. But even regardless of that, if you detected phosphine, I don't think it's a very good biosignature, because there's several different ways you can get phosphine from inorganic phosphorus compounds. So like phosphide minerals, so that's just elemental P trapped in minerals. Let's say like it only has the elemental formula of phosphorus. So like white phosphorus or black phosphorus, these phosphide minerals, if you heat them up, not even to really high temperatures, even 100 C, you can start as long as there's a proton source, so like an acid, you can form phosphine from that way. There's other ways as well. And considering that Venus kind of has some strange chemistry that's difficult to simulate in a lab, I think there's a lot left to be confirmed in terms of like how you could get phosphine. That paper looked at like thermodynamic modeling to try to explain that there's no other possible way you could get phosphine, considering the amount of hydrogen that's in the atmosphere. But there are different mechanisms that don't involve hydrogen that they didn't address.
Okay, we have another question from the audience, and it is, what chemical reactions similar to those of the Earth can be found in the subsurface of Mars?
Yeah, so you're asking what signatures you said?
Repeat, please.
Sorry, yeah, could you repeat the question? I didn't think I got it.
Yes, of course. What chemical reactions similar to those of the Earth can be found in the subsurface of Mars?
Okay. So the subsurface of Mars, there's thought to be that perhaps in the subsurface you could have some liquid water that's still there. You would have higher temperatures, so it would be more akin to like high pressure. You could have higher temperatures with some low water activity because it's in the ground. So Most similar conditions would be deep subsurface of the Earth, where you could have hydrothermal fluids circulating through the crust. So a lot of studies involving hydrothermal conditions, high pressures, and so forth would be similar. In addition to that, there's been found a lot, pretty big, what do you call it, a high amount of manganese precipitates found on the Martian surface. And so manganese is also potentially of relevance for Martian subsurface chemistry as well. So, which is also, you find a lot of manganese actually in hydrothermal vent systems. So, yeah, they could be relevant.
Okay, thank you very much.